Right, languages, because this tends to be quite a sort of mixed audience here. So what languages have we got? Predominantly Java. C, C++. Oh, real programmers. Cool. Other things, Erlang, Scala, Clojure, etc. Oh, well, this is going to be fun. Okay, I'll kick off out of politeness for sort of kicking off on time. What I'm going to do, I'm going to walk you through a number of different, the main parts of the financial services system. Again, this applies to pretty much any bank, any brokerage. Obviously, some of the brokerages just have the front and middle, and they tend to outsource to the banks for the back office. And I'm going to walk through them, and I haven't put a huge amount of technology in there. I've gone through the messaging, so what I'm going to try and do is annotate those through the talking in terms of the technologies we use in those. There's about 35 slides in total. And once we've gone through the sort of scenarios and setting the scene and looking at the sort of technologies that we've got, the problem space that we've got, then I'm going to get a little bit more into sort of some of the architecture solutions that we're looking at for this. I'm not going to go into code. This is not something where I mean, we're talking about investment banking architecture here, and from a talk for 50 minutes, we're not going to get time to delve into code. But if you want to ask, or feel free to put up your hands. Obviously, we will finish at enough time to ask some questions, but feel free halfway through, particularly with the numbers that we've got here, put your hand up. We can sort of go through some sort of scenarios and questions in detail. My background, C, C++, assembler, predominantly low latency, high performance architectures, a lot in Java. I've dabbled in most of the other languages at some points. I'm a great fan of multilingual sort of environments, so I'm certainly not against these. I don't see a huge amount of .NET in my environment, so that's probably the only part that's probably out of my scope in this. So just very quickly go through these just to put them into concept so you understand what I'm talking about. The front office is where all the trading happens. This is where typically the movies that you see, you'll see these guys sitting at a dealing room with literally 6, 8, 10 screens, and they're all displaying large graphs. They're talking to their colleagues across the phone, across internet, Reuters, that sort of thing, and they're effectively waiting for prices or triggers to change, or for someone to give them instructions to say, you know, here's the policy, we're going to sell dollars, we're going to, you know, sell this particular equity, or we want to come out of energy or move into something. And it's their job effectively to manage the bank's positions to make sure that there's not too much exposure in a particular area. So they tend to follow a crowd, and they're instructed to do certain things. So they're the people where all the energy is, and if you ever get a chance to sit or work in a trading floor, it's the most amazing sort of energetic area. If you can actually sit there and code, when I started programming, I had the great fortune to be able to sit next to traders, and I'd code stuff, and in those days testing was basically if it compiled, it ran. So you'd segment off a small number of the traders, you compile it, and you just copy it straight over to the machine, obviously distros in those days. But that's effectively where the trades are done. That's not the whole story, because that goes back down now into the middle office. Now the middle office is where a lot of the accounting happens, where effectively they're managing the risk for these, and they're defining the policies that, of course, the traders will be working on. This is where all of the interaction between the clearing, etc., happens with the corresponding banks. So if a trader has traded something from bank A to bank B, then bank A and B communicate in the middle office to make sure that these things match up. Then finally, typically, ideally the same day, but quite typically 2 or 3 days later, it arrives in the back office. Now, every time a trade happens, it doesn't immediately get paid because the traders will be trading literally hundreds of trades, often hundreds per hour. And what happens is we aggregate these up and we make one big payment at the end. So it's all part of the middle office to try and sort of aggregate up what the positions are of these things, and then finally the payments happen at the end. And of course, overnight, in an ideal bank, this is done in real time, but again, typically overnight, the process is recalculated. We work out how much money we got in the bank, what our exposure is globally around the world, what the trends are, what the currencies, what the markets have changed, etc. And we find out that we're a little bit long or short, meaning we got too much of one currency, too much of one particular commodity, and we decide the next day that this is our policy, we're going to get rid of this, or we're going to buy that. Instructions go up to the traders. They come in at 5 a.m. in the morning, pick up their instructions, and that's what they do for the rest of the day. So that's effectively the cycle. Back office is, I wouldn't say, is the most interesting part, personally, at least. I think things don't happen with the same sort of speed and that you find in the front office. So in terms of sort of interest, if you wanted to go and find somewhere exciting, start from the front office and go through to the back. If you're one of these people that just likes to turn up on a 9-to-5 job, then back office is probably the place for you. So going into a little bit more detail on these, I'm going to go through these in a little bit more. I start with the really high end. So this is the low latency, high frequency trading. This isn't so much what you find in the banks. This is effectively the brokers, the hedge funds. To them, they work in microseconds, 1/1,000,000th of a second. The time it takes light to travel 3 kilometers, if you were to build a trading engine here, let's say it was the fastest thing in the world, worked on quantum computing or something, it would still not compete with the C++ trading engines that are sitting over in the city or in the Docklands, because the time it takes to travel from Russell Square to the city exceeds the time it takes them to do the processing on these. So when these people do trading, they physically put the machines into the buildings where the exchange is. It's that important. They look for the number of routers. It's not so much the quality of the copper cable, but it's the length of the copper cable. If somebody has an extra coil in the copper cable, in case someone trips over it, that's causing latency. It's down to that sort of level of obsession. The thing is here, these guys are trading unbelievable amounts of money, hundreds of millions, billions. If they can notice a difference between somebody buying and selling something, maybe $500 million, euros, pounds, and they can notice the difference of that in maybe 0.1 milliseconds or 100 microseconds, if they can buy and sell in that amount of time, they can make a huge amount of money. But if someone beats them to it, they could lose a huge amount of money. So it's not how fast you are, it's being faster than the competitors. So when we talk about real time, it's effectively making sure that you are faster than your competitors. And so as the competitors continue to work in this environment, the time that we have to process this becomes shorter and shorter and shorter. And we're now really down to the completely crazy 3 kilometers of light speed time in terms, so we're down to sort of single microseconds in this. So what's happening is we're finding that the processing is actually done on the network card. People go out and they buy cards, these FPGA cards, which are effectively gate arrays that they program. So it's now hardware doing this, not software. So what's happening is the messages are being decoded in these gate arrays, which is firmware, if you like, and then confirmations can be sent out. We can aggregate the feeds, the amounts, etc. So this is the sort of realms that they're working in. You can forget Java in this environment. This is really not an environment for Java. In the banks, however, your average bank, they have a different sort of clientele. They're not looking to perhaps make a massive amount of money in a literally a thousandth of a second. They're looking for, their clients are much larger corporations that want perhaps a lower but more secure investment. So they're not looking for these perhaps crazy amounts of return for 15-20% on their investments. They're looking for a nice regular steady 2 or 3, 5% these days is quite good. So on your average bank, millisecond is quite reasonable. So if we're working sub-millisecond, that's great. If we're working in 3, 5, 10 milliseconds, that's generally quite acceptable in this realm. And in this environment, we find a lot of FIX. FIX is the standard that tends to be used in this area. So if we move across to, in the banking environment, outside of this sort of hedge fund environment, this is where we can start to get into the realms of using languages programming languages as opposed to hardware. If we were standing up here talking about the different cards, it's literally down to the manufacturers as opposed to the work that you and I could do in terms of optimizing this. So what they're effectively trying to do is to take all of these different feeds from various different exchanges, the London Stock Exchange, New York Stock Exchange, Chicago, etc., etc. They're taking the prices that are often quoted across all of these different feeds, aggregating them, and then trying to if one client comes in from New York and another client comes in from London wanting to buy or sell the same thing, if they know what all the prices are across the various different exchanges, they can match those trades without having to go to the exchange to do that. So we effectively have these crossing networks, crossing exchanges, which means they can match the exchanges within the bank, and that's effectively what they're trying to do. So these brokers are now connecting to very large numbers of exchanges. This is a fixed message. Anybody, I know you recognize the fixed messages. It's not particularly complicated to look at. Any programmer pretty much in any language would look at this and think, no, I could parse that, so it's 5 minutes work. Fair enough, yes, you'll parse it. It's tag value pairs separated by a control A 01 hex character. And as you can see, you've got tags numeric. The values are effectively ASCII strings. Problem is that this isn't quite as simple as it seems. It actually has a lot of repeating fields in it. So when you see one of these particular numbers, that might be a field which is repeated several times. It may be multiple payments, for example, on an interest rate derivative. It might be 2 parts of a foreign exchange. If the foreign exchange has an intermediate currency, it might be the 3 parts: buy one currency, sell an intermediate, buy the intermediate, etc. So this starts to get complex. To give you an idea of this, a trade capture report. This blur here is effectively the trade capture report in its hierarchy. So we have the parent, 3 little bits you can just see as a couple of pixels here on the screen, but we have the header, the body, and the trailer. Obviously, you can see that. Now, naturally, the vast majority of this blur here is the body of the message. Most of these are optional fields, but you have to account for them. If you're going to store these in a database or you're going to process them, you've got to account for these. So if we look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9 different levels. So we're into a pretty nasty relational database if we were going to store this. And that's basically the sort of an enlargement of it. So if you're trying to parse that, although you'll be able to parse it, if you're just thinking, oh, I'll just create a hash table and create hash values in this, it's not going to work because you're going to end up recycling and reusing a lot of these. So it becomes a little bit more complex. Middle office is much lower latency. This is where things start to get a little bit easier to understand architecturally, but a lot more complex when it comes to the complexity of the message. That fixed message was nothing compared with the sort of stuff we have in the middle office. This is where, if you're doing an interest rate derivative, for example, you've got multiple buys against multiple sells. You're selling multiple payments over a period of time, and each of those has payments attributed to it, and when those payments are, the conditions of those, and what happens if you default, and what the amount that you pay back is in terms of how it's defined. And these are defined in a thing called FpML. So this FpML itself is nicely defined. So we've moved into the realms of something fixed, which is basically designed specifically for low latency, into something which is defined now, which is complex. So the complexity is now, in this particular case, defined in schema. And give you an idea of the sorts of storage volumes when we're sort of picking this. This is one of the problems that we have. Now, if you're trying to show that you provided the best execution, for example, for your client, you've got to store all of the fixed messages. You've got to store all the prices. You've got to store, obviously, your internal messages. So to give you an idea of this, the sort of volumes that we're talking about, a fixed message is typically a few hundred bytes, but let's say it's 512 bytes for easy calculations. 100,000 a second is not unusual. It's quite a common feed, so we can sort of work on that. That's 50 megabytes a second. Now, most disk drives will store that nice and easy, but that's per channel. And you'll have multiple channels in an exchange, and then that's across multiple exchanges. So we have one client which is hooked up to 28 different exchanges. And now you're looking at sort of 4 terabytes an hour. We're looking at 1.5 gigabytes per second. Even on SSD, that's starting to get into the realms of sort of difficult. So it's the sort of thing where we're starting to have some interesting challenges, even with today's existing hardware for these sorts of things. Not only that, but you've now got to generate the indices on this. It's all very well storing the messages, but if you imagine after a year you've got 8 petabytes of data, if you can't find the message that you were originally looking for, you're going to spend an awfully long time searching through 8 petabytes of data. So you've got to store the indices. You've got to partition this up and be able to work on it. Another thing that you want to do is you want to do backplaying. So we want to store the messages. Let's say we have a complex event processing engine that we've got a scenario, an algorithmic trading scenario, where we want to say, well, something happened last week, and if we had put this into practice, we could have made some money. And that's the theory. So, how could we test that? Well, let's take last week's data and let's replay the data we had with this new theoretical scenario. So you've got to then go back. If we're looking at 36 terabytes a day, you've got to go back in and load that 180 terabytes for the week's data, and then trawl through it and then prepare what you want to test that scenario. So it becomes an interesting challenge, and typically we do that up in something. We load this stuff up to EC2, and it makes it much easier. We can use the sort of elasticity of the cloud to process and prepare this data. So we say, these are the dates we want, these are the fields we want. We can prepare that, and then we can send it back down to our local machine where we can actually run through it and test it, which is typically what we do. So in the middle office, this is where the complexity is, where you've got sheer complexity of the messages, where we've got banks with literally tens of thousands of clients, and each of those clients have hundreds, thousands of, or tens or hundreds of portfolios. Each of those portfolios have tens and hundreds of different equities. I'm sure most of you, I'm not sure most of you, in fact, some of you probably got pensions, some of you have probably got investments, and those investments will be sort of 10% Asia, 80% European equities or something like that. But each of those are managed by banks, and they decide to come in and out of the different commodities. And those effectively is a lot of what the economists are trying to work out to make the best return on these. So these things have to be bought and sold. The problem is when you suddenly say, right, I want to move out of, let's say, energy in Asia, and I want to invest in stock in South America, for example, it doesn't just happen, right, let's sell $100 million in one and buy 100 million in the other, because you have to send out the instructions, and you've got thousands of traders who are executing these things, and when they put out the orders, they're only filled, i.e. they're only exchanged when someone wants to buy them or sell them. So you never know the actual price that it's like you selling something on eBay. If you suddenly decided you want to sort of sell everything in your room on eBay, you won't know the price you're going to get for it until you've actually sold it. And so this happens in little bits. And sometimes you might want to sell it as a job lot. Here's my entire Lego kit. Thinking of my kids here. So here's my entire Lego kit, but there's someone else might want to buy it in little bits and pieces. I want all the red bricks. I want all the the car kits, etc. So again, it's the same with the trades. You might want to sell $1 million worth of one trade, but other people want to buy 100,000 of something, and you get these little bits. So it becomes very complicated, and this is where all of the different parts of the trades need to be hooked up. So the complexity of this, we have a lot less messages, typically in the tens to hundreds per second going through this. But you can see the sort of level of complexity that we get. And this is where we find a lot of grid computing. The banks were grid computing many, many years before cloud or the name cloud was associated with what we have today. In those days it was fluffy things up in the sky. They typically buy thousands of CPUs, and they'd run these things. They'd use coherence, gigaspaces, terracotta, all these technologies that were around almost 10 years ago now. And these have become common practice. The vendors have now spotted this, and that now goes on into retail and various other areas where, of course, they're selling these solutions. So what we've got to do is to process these complex events. We can't simply put these 5 to 15, sometimes 20 kilobytes of single messages into a grid and expect to process them. FpML is a good example. It's literally, 15 levels of hierarchy, over 3,000, sometimes 4,000 different elements. I wouldn't say a lot of those are optional. A lot of them are actually mandatory, so it gets quite complex in these things. Another new standard, which has been used more and more these days, and is one of the most sort of widely used canonical formats, starting to be used across all of the banks and starting to become the standard definition for a lot of these things like corporate actions is ISO 20022. It's the definition of, SEPA is defined on this. Has anybody used 20022 here? So 20022 is an interesting standard. SWIFT originally was defined on a standard called 7775, and then 15022 and 20022 is the new one. Now 20022 doesn't define any messages, it just defines the metadata behind those messages. So when you have the messages that the banks are using for SEPA, for example, for payments, for corporate actions, those are defined using the metadata repository of ISO 20022. So it's a very good repository for defining standards. It's a sort of a standard for standards, if you like. But as the European area, the Eurozone, they have to now use, or they're moving to SEPA for their payments between the various different countries. So it's a huge change for someone wanting to pay money from Spain to Germany, for example, through a French bank, and they all go ultimately through SEPA. There's one extra complexity on these messages, just because you can understand the messages, and any one of us might choose any particular technology like Xerxes or something to parse these, and there's loads of technologies in every language we come to choose from, is that they inflict these mandatory rules on us. And so just because you've managed to parse the message, you now have to understand and execute these rules. And there are quite often high tens, low hundreds of these rules per message. And you've got the message, but you've now got to say, if this field has this and this field has that, then you can't have this unless we have one of those. And I won't even bother to read those out for you because they're about as cryptic as they sound, but you've got to implement those. And so if you end up sending a message that does not comply to one of those rules, then your message is effectively nacked, and you'll get this nice IRD, interest rate derivative, message number 57 saying, you did not comply to this rule. Some of them are obvious. You can see this, you can sort of understand why they might have those, but these are things that you can't imply in schema. You can't check a lot of these rules in XML schema. So, very high throughput, very complex, high values, and now we've got these extra rules on top of it. Back office, very quickly, I won't go into a huge amount of this. Just the importance of the sort of what happens in the back office. If you've got $1 billion, bear in mind banks every single day, hundreds of billions of dollars go backwards and in and out of these things. Every single day. If you're late paying $1 billion, today 1% is not an unreasonable rate. The banks are charging those sort of rates on interest. You're late by 1 day, 1% in 1 day is $27,000. Or if you're doing sterling, it's 27,000 sterling. It's the same amount of money. What's worse, though, is if you're trading a currency and the currency changes by, in this case, the US dollar sterling, and in 1 day changes from 160 to 161. In 1 day, that's 0.6%, which is not unusual. We know this. You watch the currencies go up and down, sometimes as much as 2% in a day. 2% of $1 billion is a hell of a lot of money by anybody's standards. So that's the sort of reasons why we need to make sure these things arrive. If you make an error in one of those messages and you accidentally send a message off as the bank closes for payments at 4:29, and you have not put this particular message in, then it's nacked, you miss the payment date, and you could potentially be up for a very serious amount of money. And of course, the banks have to cover that. So this is why it's very important to make those payments. This is a SWIFT message. There's nothing particularly complicated about it. It's tag value pairs, as you can probably just about make out. Tags are numbers, 22F, for example. The one there in blue is 20C. That's the tag, the value. There's multiple values in this bit. Now, parsing that is, again, relatively simple, but as you see, it has multiple parts. So we've got to parse that and map that into something, but then we've got to apply the rules on top of that as well. So, the point I wanted to get to with all this was, very quickly, where's this used? Now, this is a typical bank. This is actually an architecture diagram, stolen, borrowed, whatever it was from a bank somewhere, long enough ago that it's now no longer relevant, and small enough that nobody's going to recognize it. But give you some sort of idea. Simplifying this a little bit, if if we look at the functional landscape, looking at this, we've got the front office, the middle office, and the back office, effectively. So front at the top, middle in the middle, back at the bottom. These are all the different functional parts. Each one of these boxes could itself be an entire project, could have 20, maybe even 50 people looking after it. It could maybe have 1,000 CPUs behind it. Some of them will just be one machine. Some of them are very commonly one laptop sitting in a corner that nobody dare touch because it's the only thing that runs it, and it's been there for 15 years. I've seen an awful lot of those, quite amusingly. And then they say, oh, could we virtualize it? And then you can't find the diskettes that you need to actually install that particular version of Windows 3.1 or something. Yes. So a 3.11, what was it? Some weird version of Windows networking or something. But there's a lot of those, and it's quite common. And we take one transaction, all the bits that it particularly touches, the different types of messages. So we see the fix predominantly in the front office. A lot of common delimited files, so these are things we can't ignore. Blue parts, proprietary XML, so these will be internal XMLs, quite often ISO 20022, some of them will be FpML. And then finally, out of the bottom, you'll get, for example, Swift coming out of there. But that's one transaction and all different parts that it would touch as it goes through the bank. Okay, not too bad, quite a lot of work to do. The problem is that goes across multiple geographies. And we're now working in a global environment, so you've now got to manage your risk and all of the different payments across all of those geographies. And then each of those, of course, because we're working in a banking environment, the whole point of banking is that we exchange money with other people. So of course that then adds all of the corresponding intermediaries and etc. And again, all of those introduce lots of different standards. So that gives you some sort of idea of the large amount of complexity that keeps certainly myself and gives you guys lots of opportunity to go into these banks, which still today have all the money, despite the fact that they're very good at losing it or spending it on houses that don't exist and those sorts of things. But there is still plenty of money there. And of the 30-odd years that I've been in banking, through numerous recessions, they still seem to have money. And because, as I said before, they compete with each other and they only remain in existence while they compete, they're looking for these technologies. So it's this tremendous opportunity and quite exciting to work in these things, to sell them and work in these areas. So let's look at a few solutions around this and how do we sort of get around some of these bits. One of the things that we've come across over the last, I don't know, 15 odd years, I suppose. I suppose we were doing it, even 20 or more years ago, but it was slightly different. We were using macros in C++ in those days in a little bit sort of slightly different way, and even in assembly we were doing self-modifying code, but it's getting out of that into reality. In the Java world, we can actually generate Java. This isn't unique to Java, obviously. We could generate Scala, we could generate F#, for example, but in the world that the banks are today, they're predominantly, middle office is predominantly Java on Linux, Java on less and less Unix, but what we can do is we can generate the Java, because the Java is then compiled, runs inside the JVM, and is often just-in-time compiled as well. So it runs extremely fast and is almost the perfect language, certainly the perfect environment, because I saw the number of people here are not necessarily Java programmers. So when I talk about Java, I sort of tend to include Scala and JRuby and anything else that sits and runs in the VM, but in real life, it tends to be Java. We'll use the DSLs on the outside, and I see those more and more coming in, but sitting on the Java side. So what we're doing is we're going back to those messages. You think back to the fix, the tag value pairs. If we can map that fixed message into a Java message, we can create effectively a large array of objects which have the tags, and the tags actually have the names. We could call it field 8, field 9, field 10, etc., whatever it may be. But when we want to get those, we can use the getters and setters. We could potentially put those into the name. So as the fix protocol defines those messages, we can then map those into the generated Java code. As objects, if we then redefine the serialization of those, we can actually make them very, very efficient. Not quite as efficient as fix, obviously, because it's designed purely for that sort of efficiency. But it does mean that if it's already in an object, we don't need to consistently reparse it to get the values out. So we don't have to go through the object, parse it, as you would with a SAX parser in XML. It's effectively like going from, if you're treating XML, you've got a number of options. You can use, obviously, SAX, it's very fast to go through, find the value you want. If you're picking up many values, you'd be better to convert it into a DOM, for example, where you can go back and get the values very quickly. DOMs aren't particularly sort of program friendly. You've got nodes which have nodes, and node lists and these things. And so the programmatic approach to that is rather tiresome. So we tend to use binding. We use JAXB, JibX, Casa, these sort of things. And what it does is obviously generate the code based on the schema. We can go back in and now pick out the values. So it's exactly what we're doing now. So we Java bind fix, we Java bind obviously the XML, and we can Java bind the Swift. So that makes it very, very fast and very easy for the programmers to work with. So if we take the comma delimited file, I remember going back to what we were looking at before, we take a comma delimited file. Now, where any programmer can parse this in 5 or 10 minutes, start to add a few rules on this. So we could add some obvious rules. I'm sure some of you know these credit card numbers have to have what's called a LUN check, so they have to have a mod 10. So basically, the last digit means that they have to be all add up, divisible, with no remainder from 10. Obviously, you'll know from a credit card that the payment date must be before the expiry date. Now, these are rules that you've got to follow. So if you were reading this comma delimited file, effectively, you've got to add these rules on top of it. This is not dissimilar from XML from anything else. So this is just the most basic sort of stuff. So if we can map this comma delimited file directly into Java, we can add the rules. Interestingly, though, regardless of whether this is a comma delimited file or XML or fix, obviously you're not going to get credit cards in fix or whatever it may be, the rules remain the same. So what you have to remember is, if we go back to a metadata concept of this, if we go into, for example, ISO 20022, I'm using credit cards because it's easier to understand. If we can define the basics of credit card transactions and payments, the rules are the same regardless of the way that it's transferred between machines. So if we're doing comma delimited files, the payment date must still be before the expiry date. The credit card number must still be the same. It doesn't matter on the format. So what we now do is we create a metadata repository that defines what is a payment date, what is a credit card number. We define rules on the credit card number, and we define rules on payment dates and expiry dates. And so we now start to create a metadata repository around credit cards. And again, I'm using this as a simplistic example. But it does mean that as we process credit cards, let's say if we were doing it from the front to the middle to the back office, the rules remain the same all the way through. So if we're working in a trading environment, we take our fixed message here, we're reading out a date, in this case field 52. It doesn't matter the fact that it's displayed in ASCII in this particular case. It could equally well come in XML in a ISO 8901 date or whatever it is. In fix it comes in a different, in Swift it comes in a different format. But if we can now say that these are in fact both the same date, all of the rules start to reapply. So we can now start to use this technology to apply the same logic regardless of the format it's in. So this is how we don't do enterprise integration. I think everybody learned this lesson a long, long time ago. You don't simply just map everything to everything else. But pushing this into a bank might seem the obvious way, where everything goes into a canonical format, but it does actually become more complex, because what happens is you end up with a project up here that was started 3 years ago, and you change the canonical message because these guys are now trading something different. Now these guys now have to change their message type that goes across here, but they don't have any budget because that's a project that disbanded 3 years ago. And so now you have this problem of multiple canonical messages going up and down your system, and then very, very quickly you end up with this sort of mess with canonical messages here, 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 and here, for example. And so it's very hard to sort of push through this concept. So what we try and do is basically create a metadata repository. We used FpML for a number of years because it was about the best thing that was defined. Today, most banks are looking at ISO 20022 because it's defined for that specific reason. we take the various different formats. So here's fix as an example. Here's a date format, and we basically say this is a payment date. We can do the same with the SWIFT. SWIFT is defined on a similar standard, so it's much easier to do that. And this, well, SWIFT actually managed the ISO 20022, so it does make life easier. But if we say this date is the same as this date, we can now follow through from front to middle to back office all the different parts of the trade as we go through. So what it means is, when we come back to our integration, a lot of the mapping from here across to the canonical format, we've already mapped what half of the fields are in here. So we can start to do auto mapping. We know that this date is in fact the date defined by our standard. We know that this amount is the amount defined by the standard. So a lot of this messaging, canonical interactions gets done for us. So effectively what we do is we model every message, any endpoint, any internal, external. We create Java binding of that. And it means we can now create a bus, which is predominantly Java objects. If we're doing high-performance computing, where we're modeling, for example, complex derivatives and looking for various different, say, numbers out of that, effectively, because it's in Java, or because it's in a language that we can understand, we don't need to parse it. It's already effectively parsed. If we do get price, it comes back with a double. And it's much, much quicker than trawling through the message again, reparsing it, and converting the ASCII back into a double. The messages we're typically using, there's very point in creating yet another standard. So what we're trying to do generally is to map these to existing standards. And a lot of the banks are now, something we did at JP Morgan Chase, we created a IBML, Investment Bank Markup Language, and it was based on FpML. And then, of course, as we found things that didn't map into FpML, we had a lot of the people that were working on the FpML standards, we would then commit those back into FpML. So we start adding to the standard. Same sort of thing is possible with the ISO 20022, so you can start to create new sort of effectively requirements around the ISO 20022 standard. So these are the messages that are now being created. But what's important again is we're now adding the validation to these messages. So if a payment date and a settlement date, obviously the settlement date is always after the payment date, but that's the same in the front office, the middle office, and the back office. These rules get carried all the way through. Persistence is much easier doing this way. We don't need to map these horrible messages into relational databases. One of the most fun exercises I like doing when people say, Oracle rules. Yes, it does. It is definitely the best relational database I know out there. It's great. But try putting one of these 3,000 element messages into an Oracle database. Yes, you can do it. And I've done it, and it's very easy to do. You can use JPA, Hibernate, whatever you want to generate the code. Then try changing the message, and it changes the tables. Then change it again. It changes the tables again. Now try reading an old message, the first message you had, the second, the third, and the fourth, each of them which is different, and try and store all of those at the same time. You'll end up with a new schema every few weeks. And this is the main issue that we have with the relational databases, is being able to follow these. And like I said before, we were doing sort of internal cloud computing before. What we were doing was effectively putting these complex messages into databases as clubs and retrieving them. And today we have technologies like MongoDB, Redis, etc., that will do this for us and make it much more efficient. So last couple of slides here. Effectively, when we walk into a bank, certainly as a service provider, or you go in as I would as an architect or something, the business people have got a particular solution in mind. They want to go from the left-hand side to the right-hand side. With a new line of business, for example, I've got messages coming in here, I want to do this, that, and the other, I want to process them, I want to see what I've got, and I want them to pop out the other end. And then you're going to go back and say, well, that's actually 5-man years because we've got fix on here, we need to understand that, and we've got to apply all the rules, then we've got to model this into FpML to hook up with the middle office, then we've got 6 different formats of comma delimited files coming from your corresponding counterparties, and then finally the output's got to go out in Swift. So something which is predominantly simple becomes horrendously complex. And so this ability to now model all of the different messages using a model-driven architecture into a metadata repository is vastly reducing a lot of the time that we spend in the banks and keeping up with the performance requirements and that we have. So last slide, I wanted to just give you a couple of sort of tips, and I'm sure you know most of these, but from a number of years of practice, keep it simple. The other S is supposed to be keep it simple, stupid. So keep it simple. I'm a great fan of if you can do something on a command line in Unix, then do it. Don't invent something around it. You see people they have a technology and they try and use the technology to do something when it's not designed to do that. There are technologies been around for decades that do these things. Object relational mapping. It's one of the things that adds anything up to a third, sometimes half of the entire complexity of your applications. You're working in an object-oriented programming language, usually, and then people work on relational databases, and the bit that goes between them is the vast majority of the complexity. Distributed architectures. You need performance these days. If you're working in a sort of resilient, redundant, high availability architecture, you can't do that on one machine. You need to program with the concept of your objects being distributed. Even if it's internally, multiple VMs, multiple virtual machines on the operating system, and multiple Java virtual machines, for example, or .NET, whatever it may be. But you need to have this concept of a distributed architecture. Akka, as I'll mention in a second, is very good at providing a framework for that. The model-driven architecture I've mentioned before. So frameworks I see used increasingly, and quite, it gives me great pleasure to see these when you go into a client, they say, oh, we've designed all this around a sort of an actor-based concurrency architecture, and we're using Akka. And you just think, they've got the right idea, it's going to work. It gives you a great framework for modeling this sort of distributed architecture. So unfortunately, the only talk I probably would have turned up for today, including mine, would have been the Akka talk, which is on in parallel. So I apologize for keeping you away from that talk, because I think Akka is going to be a great future in this world. Test. I didn't know really how to put this. Test code, test code, test code. It's amazing how many people will sit down for 2 months and code and not test it at the end. Make sure you work on an iterative basis. Some of these processes for Swift messages, for example, we generated 88,000 tests for these, 88,000 different tests. So we go through these regression tests, and because we've got high performance, we can run through those 88,000 in a minute quite easily. So it's the sort of test scenarios that we're pushing through these things to make sure we don't cause problems. We test the performance too. Transactions. People get obsessed with transactions. You can work on compensational transactions. You put 1,000 messages in. If you don't get 1,000 messages out, something went wrong. Go back and fix it afterwards. Things don't generally go wrong. If they do, go back and compensate afterwards, or go back and fix it. But if you start a transaction, particularly a distributed transaction, you are just going to cause yourself no end of problems. And for every time that I've been called into a large architecture that's having problems in performance, 9 out of 10 times it's because somebody's started to say, oh, if we send this message, we want to make sure it ends up in the database. Therefore, we're going to start a transaction here, and then we'll follow that onto there, and then into the messaging system, and we'll use an XA compliant one that goes into the database, and we'll write it. And they get 5 messages a second through. You take all the transactions out, count the number of messages that go in, count how many you got in the database, and if you're missing one, go back and start it again. It's still quicker to run the entire day's messages through than it is to mess around with the transactions. You can get 1,000-fold in performance by taking transactions out. So think an entire life without transactions. Multiple languages. As I say, I'm a great fan of these. I'm not particularly good at programming in Scala or Clojure, although I've dabbled in them, and I've started to get to like Scala quite a bit. But I think they have a really important place. The same way as if you go into any bank, you'll find people using Excel. If people think in terms of formula using Excel, then that's what they're going to use. And unfortunately, that's the reason why Microsoft is still stuck in banks, is because they were clever enough to provide Excel spreadsheets, and they're here to stay. So if you've got a language which is better at doing something, then use it and stick with it. And the object relational mapping as well, which I know I've mentioned, but I'll mention it again. Object relational mapping is probably one of the sort of biggest causes of code. I hope I've covered some bits that have kept some of you awake. I know it's the session after lunch and the heating was turned up to 26 degrees when I walked in, so it's been hard to stay awake. So if you have any questions at any level of depth, please fire away. Yes?
So you mentioned that defining validation rules and defining on the front office, middle office, and upper office. I was just interested, are you still able to get the real-time requirements or performance that you were talking about?
So on the validation rules, so you're asking where we find the requirements for the validation rules?
No, so you mentioned that when you're working at various stages of different requirements for how long you can take to process certain tasks. And for some of them, you need like one microsecond.
Right.
And so I was interested, are you able to do that kind of real-time processing with the Java-based implementation?
If we get down into the microseconds, no, Java's not, we don't see Java in that sort of area at all. In the milliseconds, yes, we find a lot of areas in that. And so how to measure the performance is a totally different game, because it's almost like a Heisenberg thing. If you start putting in measurements, you start to affect the performance. But it's, yes, and it's interesting to see, we, for example, have taken messages like Swift messages or fixed messages and we put validation in, and then sometimes you find, because we're using the simplicity is to use something like XPath to do validation. So you say if this field, you can supply XPath for it, is greater than this field, then message fails. But then you find out that the XPath, because somebody's used // for example, takes a long time to evaluate because it's got to tree walk the entire message, and you find the validation takes 10 times longer than the parsing of the message. So it's interesting when you parse messages through. Frequently we'll take a flow, we'll read the messages in, we'll read them into memory, so we'll take 1 million messages, read them into memory, then we'll parse them, then we'll validate them, then we'll transform them. And so in each part you measure it, and generally we're a sort of 45-man company, reasonably good turnover, but we're not one of these sort of US companies like Tengen that gets $75 million to sort of sit around and spend it on lots of nice things without actually having sort of necessarily revenue. I'm sure it'll come because it's good technology, but we tend to follow what a client wants, and so we won't optimize a message until somebody says we need this to go faster. So if, we'll process fix. If it goes fast enough to demo and use, we'll use it. But if a client comes back and says we need it to go 10 times faster, then we'll go back in and optimize it. And that will frequently mean writing those validation methods in Java, for example, or Scala or something that compiles at least, because XPath is not the best one. Another question there.
You said that you always have to be faster than the competitor. So how do you actually help measure this? I mean, through being the consultant for both, or was that?
Good question. I won't repeat it because you've got a microphone. It's a good question. It's a very secretive environment, so you'll be surprised what they do. There was something quite recently where I think one of the large exchanges, the New York Stock Exchange, had 10% of extra traffic on it, and it was basically somebody that was just doing almost a denial of service attack just to slow things down so that they could see how other people's behaved. There were other things they do. When I started in the environment, traders used to take let's say $1,000 deal, and they divide it up into $110 deals because they used to get commission for everything that went across the Reuters network. These days, they're automatically traded. So what will happen is people will put out fictitious trades, or they'll take something which doesn't really matter, and they'll see how other people's machines react. And you've got people with Asperger's syndrome that are sort of all sitting down there that, sort of like this, working on their, in R and MATLAB and things, working out ways of perhaps trying to fool someone else's machine. So it's an amazing world. It really is fascinating. Every time you go back, you see somebody coming up with some new idea of either purposely slowing down someone else's machine or trying to get a little edge or creating something fictitious. It's really fascinating. But to find out how fast someone else is going, you don't know until you start to make more money. So it's a bit of a gamble.
Awesome. Thank you.
Any other questions? Okay, I think... oh, yeah, we have a question, sorry.
Maybe you can show the slide of the transaction flow.
That one?
No.
Before?
The The one with the arrows and different schemas?
Another one. I'm looking for arrows.
No?
No.
I think it was this one. There was one like this with the arrows. Yes,
one.
this one.
That one.
So this is sort of the flow that the transaction goes through. I understand.
It's a typical transaction, yes.
Yes. So my question is, how do you scale and configure all these different services to work together?
How do we scale this? This is a good question. This is a very asynchronous environment. So effectively, as stuff goes down, everything's in queues. There's no synchronicity on this at all. That's obviously one way to scale it. So each of these can scale in its own right. As a trade is made, it may go onto risk control, for example, or will look, well, in the risk, for example, you'll be doing a lot of computation in there, but the result of that doesn't necessarily have to be used further on down. We've got payments, we'll be going off for the matching, for example. All of these are asynchronous flows between the external parties as well. There was a thing about 10 years ago called GSTPA, the Global Straight-Through Processing Association, and it was trying to define the interaction, and it's using choreography as opposed to sort of, you're not managing. One of the differences with trying to manage this as sort of work streams, to say first you go here, then you go here, then you go here, then you go here, is that this is so asynchronous and everything's completely independent. It's based on a event condition action. I get this event on this, given this condition, I perform this action. So it's choreographed. Each one of these behaves independently, and I think it's been around for a long, long time. It's been a human process for hundreds of years. The banks have always done this for hundreds of years, and I think it's a very good model to scale out. And it's the sort of thing where retail these days has never had the scale. You go back 20 years ago and retail was just done, just didn't have the scale it has today. Amazon didn't exist. Banks did exist, and so I think they've taken the human model and they've scaled that, and it scales very well. Any other questions? Yeah, another one over here.
One JVM specific question. I saw your presentation a few years ago, and you were talking about Azure systems.
Oh yes.
What's now? Are you using Azure systems now?
No, we're not actually. I was a great fan of the Azure system. We did some demos on Azure, and now they've created effectively a software version of that. And I would have tried it if it had worked at the time on Amazon, which it didn't, and it didn't work on my Mac either. So in terms of trying it out, I know a lot of banks are trying it out. So it is a popular option. But again, I think they promise whatever it is, 20, 30%. I think that's good. But there are still banks, I can give you two very, very large banks that still work on Java 1.4. When I was at JP Morgan Chase, I forget which version it was, but we justified moving from 1.3 to 1.4 on the 20% performance increase. It saved tens of millions of dollars on the number of machines we were able to reduce in production based on the performance. So moving from 1.4 to 1.5, et cetera, if Azure is another one of those steps, that's fine. But banks with production where they're charging typically $20,000 per machine per year, to be able to save machines is massive, but the impact of using a third-party software is risky, perhaps. I think, just for fairness, we'll cut it there, so thank you very much. If you have any questions, please feel free to come up and ask me afterwards. Thank you.